The Andromeda Galaxy holds a secret in its ghostly outer halo. This immense sphere of ancient stars and dark matter, stretching nearly 1,000,000 light-years into the emptiness, is our nearest galactic neighbor's most mysterious frontier. We are about to journey into that profound darkness to uncover 50 of the strangest objects ever detected there. By the end, you will see our cosmic backyard not as empty space, but as a gallery of the universe's most bizarre relics and riddles. We will encounter rogue planets sailing through eternal night, invisible clumps of pure dark matter, and structures so unusual they hint at intelligence beyond our own. What forgotten stories do these silent wanderers hold, and what do they reveal about the raw, ancient forces that built galaxies? What single object in the cosmic dark would you most want to see for yourself? This journey begins with a world that should not exist. Drifting in the absolute cold between the halo's ancient stars, a solitary wanderer was caught in a fleeting cosmic alignment. Astronomers witnessed a distant star in Andromeda's disk momentarily brighten, not from its own light, but from the subtle warping of space-time itself. A massive, invisible object had passed directly in front of it, acting as a gravitational lens and bending the starlight toward us. That object was not a dim star or a black hole. The data pointed to a solitary planet, untethered from any sun, sailing through the galactic halo's perpetual dark. This was the first confirmed rogue planet in another galaxy, a gas giant perhaps many times the mass of Jupiter, cast out from its native solar system in a long-forgotten gravitational upheaval. Its discovery was a whisper in the data, but its implications are a shout. If one such world can be found in that vast emptiness, how many more are there? Billions, trillions, the space between stars and even between galaxies may be filled with these orphaned worlds. Picture the environment of this lone giant. Its sky is a permanent, star-studded black, devoid of a sunrise for billions of years. Any hypothetical moon orbiting it would know only the faint glow of distant island universes. Yet within such a world, life is not entirely impossible. The crushing pressure and radioactive decay in its core could generate immense internal heat, potentially maintaining a vast, hidden ocean beneath a frozen crust of exotic ices. In that sunless abyss, in eternal darkness kept liquid by the planet's own heart, who knows what chemistry might unfold? This first object sets the tone for our entire exploration. The halo is not empty. It is a graveyard of solar systems, a reservoir of lost worlds, and each one is a story of cosmic violence and lonely survival. That orphan planet is a solitary ghost, but the next object is a ghost city. Deep within the halo, astronomers have mapped a sprawling, faint smudge of light that resolves into a globular cluster of staggering age and purity. This is not a typical dense ball of stars. It is immense, diffuse, and holds a secret in the very atoms of its ancient suns. Its stars possess an almost impossibly low metallicity. In astronomy, metals means any element heavier than hydrogen or helium. The stars in this cluster have almost none. They are composed of 99.9% pure hydrogen and helium, the primordial fuel of the Big Bang. This makes them the closest thing we have to a living fossil from the universe's first few 100 million years, a time before supernova had forged the carbon, oxygen, and iron that make up our world and our bodies. This cluster is not just old, it is pristine. It is a preserved sample of the universe's original stellar building material, a frozen moment from an era when galaxies were just beginning to coalesce from the cosmic dark. Its diffuse, spread-out structure is equally telling. It suggests this cluster was never tightly bound to Andromeda's bustling disk, but instead formed in the quiet outskirts during the galaxy's violent birth, and has been orbiting in the halo ever since, largely untouched by later mergers. This presents a direct challenge. Current models of galactic assembly suggest the halo should be built from the shredded remains of many smaller galaxies, each contributing their own more metal-rich stars. Finding such a massive, pure, and intact relic implies that some of the universe's first structures survived the chaotic construction process wholly unscathed. It is a foundational piece of Andromeda that was never broken apart, a silent witness to everything that came after. To look at this faint smudge is to look directly at the infant universe, a collection of stars that have shone with the same simple, pristine light for over 13 billion years. What stories could they tell if only we could listen? That pristine cluster of ancient stars is a monument to the universe's first light, but not everything in the halo is so luminous. Our third object is a whisper so faint it nearly dissolves into the cosmic background static. It is an ultra-faint dwarf galaxy, a smudge of a few thousand ancient stars held together by a secret. Its total light output is less than a single bright star in our own Milky Way. If you stood on a planet within it, your night sky would be almost empty, punctuated by only a handful of dim, old suns separated by vast gulfs of darkness. Yet this fragile collection survives, orbiting the colossal Andromeda galaxy without being torn apart. The math reveals why, and it points to the true nature of the halo. This dwarf's visible stars account for less than 1% of its total mass. The rest, over 99%, is an immense invisible sphere of dark matter. This dark matter halo acts as a gravitational anchor, a deep well of unseen mass that holds the few visible stars together like flies trapped in amber, protecting the entire structure from the tidal forces of its giant neighbor. This presents a profound puzzle for scientists. The dark matter in this ultra-faint dwarf appears to be very cold, meaning it moves slowly and clumps together densely at the galaxy's center. This supports one major theory about dark matter's nature. But if that's true, then our computer simulations of the universe predict there should be hundreds, even thousands, of such dark matter-dominated dwarfs around every large galaxy. We only see a few dozen, so where are all the others? Are they there but too faint for our telescopes? Or does this mean our understanding of dark matter's properties is incomplete? This nearly invisible object, then, is not just a curiosity, it is a critical laboratory. By studying its subtle motions and structure, astronomers are not just looking at a failed galaxy. They are probing the fundamental particle that makes up over 80% of all matter in the universe, the invisible scaffold upon which all galaxies are built. This faint smudge of light is, in truth, a window into the deepest and most dominant unknown in all of physics. Dark matter is the hidden anchor of that faint dwarf galaxy, but sometimes it gathers in places with no stars at all. Our fourth object is a phantom of pure gravity, a massive, invisible clump of dark matter drifting alone in the halo's depths. It was not discovered by any light it emitted, for it emits none. Instead, its presence was betrayed by a subtle distortion in the fabric of space itself. Astronomers were studying a distant, far-off galaxy far behind the Andromeda halo when they noticed its image was being stretched and warped into a faint, elongated arc. This phenomenon, called gravitational-lensing, occurs when a massive object's gravity bends the light from a more distant source, acting like a flawed cosmic magnifying glass. The map of this distortion revealed the culprit, a concentration of matter with the mass of a small galaxy. Yet when they looked directly at that spot in every wavelength of light, from radio waves to X-rays, they saw absolutely nothing. No stars, no glowing gas, not even a wisp of dust. This was a dark matter clump in its most isolated and pristine form, a ghost of pure mass sailing silently through the void. Mapping such an object relies on painstaking statistical analysis. By observing how the images of thousands of background galaxies are minutely distorted, scientists can create a mass map of the foreground, revealing the invisible topography of dark matter in stunning detail. This particular clump stood out as a solitary hill in that map, a gravitational landmark with no visible counterpart. These pure dark matter clumps are a cornerstone prediction of our leading model of the universe, often called the cold dark matter model. The theory states that dark matter should clump first, forming an invisible cosmic scaffolding, and normal matter, the gas and dust that make stars, simply falls into its gravitational wells. Finding these isolated clumps confirms that dark matter can indeed structure itself independently of the bright, familiar universe we see. But it also raises a tantalizing and almost unsettling question. What exactly is inside such a clump? If it contains no conventional atoms, what form does that immense mass take? It could be a dense swarm of as yet unknown particles flowing through each other like a silent, intangible tide. Some theories suggest regions of such pure dark matter could even foster exotic states or interactions impossible in our matter-rich environment, a unique physics laboratory hidden in plain darkness. This invisible knot of gravity is more than just a confirmation of theory. It is a challenge to our imagination, a pocket of the universe composed of something fundamentally other, waiting for us to finally understand its nature. The halo's invisible clumps of dark matter are its hidden architecture, but its history is written in rivers of light. Wrapped around Andromeda like a faint cosmic scar is a colossal stellar stream, a shimmering arc of millions of stars stretching over hundreds of thousands of light years. This is not a random collection, it is the ghost of a galaxy. Billions of years ago, a small dwarf galaxy ventured too close to Andromeda's immense gravitational pull. Slowly, over countless orbits, it was stretched and shredded, its stars pulled out into long, graceful ribbons that now orbit in a vast, silent river around the predator that consumed it. This process is galactic cannibalism, and it is how giant galaxies like Andromeda and our own Milky Way grow. They do not just form from gas, they feast on their smaller neighbors, digesting them into their halos. The chemistry of this stellar stream is a forensic report from that ancient crime scene. By analyzing the light from these stars, astronomers can determine their unique elemental fingerprint. Every galaxy has a slightly different chemical history, based on how many generations of stars lived and died within it, enriching its gas with new elements. The stars in this stream share a distinct signature different from Andromeda's native halo stars. This tells us the identity of the victim, the specific dwarf galaxy that was torn apart. Furthermore, the stream's width and the degree to which its stars have mingled with the background halo reveal the timeline. A sharp, narrow stream is a recent merger, its stars not yet fully mixed. A broad, diffuse one is an ancient event. This particular giant stream is both broad and deeply woven into the halo, marking it as one of Andromeda's oldest and most massive meals, a foundational act of cosmic growth from the galaxy's early, violent youth. To look at this faint river of suns is to witness a galactic fossil, a moment of destruction frozen in time and gravity. It is a direct line of sight to an event that unfolded when Earth was still a molten rock, a reminder that the serene spiral we see today was built on a history of colossal violence written in the scattered stars of its halo. While stellar streams tell of galaxies torn apart, one star in the halo tells a story of individual escape. It is a hypervelocity runaway, a solitary sun hurtling through the darkness at a speed so immense it will eventually break free from the Andromeda galaxy's gravitational grasp forever. Clocked at over 2 million miles per hour, this star is not merely orbiting the galactic center, it is fleeing from it, a cosmic projectile shot from the heart of the galaxy itself. Such incredible velocities are not born in stellar nurseries. The most likely culprit is the supermassive black hole that lurks at Andromeda's core. Picture a binary star system, two stars orbiting each other, drifting too close to that monstrous gravitational well. The black hole's immense tide could capture one star, slinging it into a tight orbit, while violently ejecting its companion like a stone from a slingshot. The ejected star receives a gravitational kick of unimaginable force, catapulting it outward on a one-way trip into the intergalactic void. Tracing its trajectory backward points like an arrow directly to the galactic center, confirming its dramatic origin story. Where is it headed? On its current path, this star will first plunge through the sparse outer halo, then cross the million-light-year gulf of nothingness between Andromeda and our own local group of galaxies. It will become a true intergalactic wanderer, sailing through the abyss where the space between galaxies is so vast and empty that, from its perspective, the universe would appear as isolated islands of light in an endless black ocean. This raises a fascinating possibility. Could this star have brought passengers? If it was ejected from a stable system before the black hole encounter, it might have carried its planets along for the ride. Imagine a world, perhaps once orbiting in a temperate zone, suddenly ripped from its cosmic neighborhood and accelerated to a significant fraction of light speed. Its sun would now be a fixed point in a sky growing ever darker, the familiar constellations of its home galaxy slowly shrinking into a faint, receding cloud. For any life on such a world, the concept of day and night would vanish, replaced by an eternal starry night that itself fades over eons. This hypervelocity star is more than a curiosity, it is a test of survival. Could a planetary system hold together under such a violent launch? Could atmospheres and oceans remain? The journey of this one star challenges our understanding of stellar and planetary resilience, suggesting that even cataclysmic galactic events might not always mean annihilation, but sometimes a ticket to the greatest journey imaginable, a voyage out of a galaxy entirely. The journey of a hypervelocity star is a one-way ticket out of the galaxy, but some objects are born from an even more violent departure. Drifting in the halo's darkness is a city-sized cinder spinning hundreds of times every second, a lighthouse beam of radio waves cutting through the silent dark. This is an isolated neutron star, a pulsar, and it is utterly alone. When a massive star reaches the end of its life, it does not go quietly. Its core, crushed under unimaginable pressure, collapses in a cataclysmic supernova explosion. What remains is a neutron star, an object so dense that a single teaspoon of its material would weigh as much as a mountain. This particular neutron star is a pulsar, meaning it spins rapidly, and its intense magnetic fields funnel radiation into narrow beams that sweep across space like a cosmic lighthouse. Each time that beam flashes across Earth, our radio telescopes detect a pulse of energy perfectly timed, a metronome in the void. The story, however, is in what we do not see. Around this spinning cinder, there is no glowing cloud of debris, no supernova remnant to mark its violent birth. There is also no companion star. It is not in a binary system stealing material from a neighbor. This pulsar is a solitary relic, a clean bullet fired from a galactic gun long ago. Its isolation tells a tale of extraordinary force. The supernova that created it was likely asymmetrical, giving the newborn neutron star a tremendous kick that blasted it clear of its own debris cloud and out of its birthplace in the galactic disk, sending it sailing into the halo. We can read its life story in its spin. The pulsar's rhythm is not perfectly steady. It is very slowly, imperceptibly winding down. By measuring this gradual slowdown, astronomers can calculate the strength of its breaking magnetic field and estimate its age. This one spins fast but is slowing steadily, suggesting it is a middle-aged veteran of the halo, perhaps tens of millions of years old. For all that time, it has been traveling through the profound emptiness, its incredible density making it a near-perfect celestial artifact, unchanged since the moment of its creation. Imagine the history encoded in that spinning sphere. It witnessed the detonation that forged it, a flash of light brighter than 1 billion suns. It then sailed away from that chaos, crossing the vast gulf from the star-rich disk into the halo's sparse frontier, all while broadcasting its rapid-fire pulse into a darkness where, for eons, no instrument existed to hear it. It is a monument to one of the universe's most violent events, now performing a silent, precise ballet in the deepest quiet imaginable. That pulsar is a perfect clockwork of decay, but some objects in the halo refuse to be seen at all. Our eighth mystery is a ghost in the archives, a globular cluster that vanishes before our eyes. In photographs taken with ordinary visible light telescopes, it appears as a classic, dense ball of ancient stars, a familiar sight. But when astronomers pointed instruments sensitive to infrared and ultraviolet light at the same coordinates, they saw nothing. The cluster simply disappeared. This is not a trick of the light or an error. It means this object emits almost no energy outside a very narrow band of the visible spectrum. It has a spectral signature unlike any other star cluster known. The leading theory is that this cluster is composed almost entirely of a bizarre and ancient stellar population. Cool, helium-burning red giants that have exhausted their hydrogen fuel. These are stars in a very specific late stage of life, and they emit most of their faint light in the red part of the visible spectrum, while being extraordinarily dim in both the hotter ultraviolet and the longer wavelength infrared. It is as if the entire cluster is filled with stars that are all the same age and all at the exact same point in their stellar evolution, a synchronized chorus of aging suns. An alternative, even stranger possibility involves dust. Perhaps the cluster is enveloped in a unique cloud of ultra-fine carbon dust, similar to graphite or soot. This dust would be exceptionally effective at absorbing ultraviolet and infrared light, only allowing that narrow slice of visible red light to pass through. Where would such dust come from? It could be the accumulated debris from countless generations of dying stars within the cluster itself, a shroud of their own making. Observing this object is a monumental challenge. Confirming its nature requires comparing incredibly faint signals across multiple wavelengths, fighting against the noise of the cosmos itself. Each new observation is like trying to listen for a single, specific note in a symphony played by an orchestra 1,000 miles away. This cluster's strange behavior forces us to question what we think we know about stellar life cycles and cluster formation. How did an entire cluster of stars end up so perfectly synchronized? Could some catastrophic event have triggered a single, universe-wide burst of star formation within it, leaving every star with the same birthday and the same fate? Or does its unique shroud point to a chemical history so peculiar that it produced dust unlike anything in our own galactic neighborhood? This enigmatic dark cluster is more than an oddity. It is a cosmic fossil locked in a state we do not fully understand, a reminder that even the oldest, most studied types of objects in the universe can still hold profound and unsettling secrets. A pair of dead stars are locked in a fatal dance on the edge of nothing. Our ninth object is a binary black hole system, two stellar mass voids orbiting each other in the halo's profound isolation. We have not seen them directly, for they emit no light. Instead, their presence is betrayed by a subtle, rhythmic flicker in X-ray emissions, a telltale signature of their destructive waltz. As these black holes circle one another, their immense gravity violently strips and compresses any trace of gas drifting through the halo, heating it to millions of degrees and causing it to flare in X-rays just before it vanishes forever over the event horizon. The rhythm of these flares reveals the orbital period of the pair, a countdown to an unimaginable collision. How did such a pair end up so far from the bustling galactic disk? Their story begins in a dense star cluster, a celestial metropolis where gravitational interactions are constant and chaotic. Within such a crowded environment, black holes can find each other. They may form from two massive stars already in a binary system, both dying in supernova. More dramatically, they could be solitary black holes that are gravitationally drawn together through a complex dance, eventually forming a tight pair. This binary black hole system then acts like a gravitational slingshot. Through interactions with other stars or black holes in the cluster, the pair can receive a powerful kick, ejecting them entirely from their birthplace. They are thrown out into the galactic halo, carrying their closed orbit with them into the eternal dark. Their future is written in the fabric of space-time itself. As they orbit, they lose energy by emitting gravitational waves, ripples in the very geometry of the universe. This loss of energy causes their orbits to slowly, inexorably decay. Over millions of years, they will spiral closer and closer together, their orbital dance accelerating from a slow waltz to a frenzied whirl. The final act is a merger, a fraction of a second event where the two black holes become one. In that instant, they release more power than all the stars in the observable universe combined, not as light, but as a thunderous ripple in space-time, a gravitational wave that will propagate outward at the speed of light, stretching and squeezing everything in its path. This particular wave will ripple through the Andromeda-halo, then cross the intergalactic void. In roughly 2.5 million years, it will pass through our own Milky Way, a silent tremor in the cosmos marking the end of a dance that began in a star cluster eons ago. This invisible binary is a coiled spring of pure gravitational energy, a clock ticking down in the dark toward a moment that will literally shake the universe. Far from the orderly spiral, a star wages war against itself. This is a luminous blue variable, one of the most massive and violently unstable stars known, and it burns with a lonely, furious light in the halo's darkness. It is a true cosmic titan, containing perhaps 100 times the mass of our Sun and shining with the brightness of several million, but such immensity comes at a terrible price. The star's outer layers are so loosely bound by its own immense gravity that it undergoes periodic, catastrophic eruptions. It can violently shed entire solar masses worth of material in an outburst that briefly outshines its entire host galaxy, casting off a shell of glowing gas that expands into the void before the star, temporarily quelled, returns to its brilliant blue state. Finding such a star in the halo is profoundly strange. These monsters are born in the densest, richest stellar nurseries within a galaxy's spiral arms, where vast clouds of gas collapse to form stars of epic scale. They are not meant to live in the galactic suburbs, let alone the desolate outskirts of the halo. So how did it get there? There are two compelling stories. The first is one of exile. This star may have been born in a tight, massive cluster within Andromeda's disk. In such a crowded environment, gravitational close encounters can act like a slingshot, flinging stars out at tremendous speeds. A star this massive, if it received such a kick, could have been ejected entirely, sent on a one-way journey into the halo where it now burns in solitary, unstable splendor. The second story is even more radical. Could it have formed in place? This would require a collapsing cloud of pristine gas in the halo itself, dense and massive enough to birth a star of such staggering proportions. While incredibly rare, the discovery of such a native halo giant would force us to rewrite our understanding of where and how the universe's most extreme stars can be born. Its fate, however, is sealed regardless of its origin. A luminous blue variable is a star living on borrowed time, furiously burning through its nuclear fuel in just a few million years. Its final act will be a supernova of almost unimaginable scale, a hypernova or a gamma-ray burst progenitor. When its core finally collapses, it will not go quietly. The explosion will likely create a black hole and may fire a focused beam of high-energy radiation across the universe. For a brief moment, this solitary exile will become the brightest point in the local group, a final, defiant shout against the dark that birthed it, a transient monument to the violent beauty of stellar life and death. The fury of a dying giant star is one thing, but the death of a star like our own Sun is a more intricate, beautiful kind of violence. Drifting in the halo are two ghostly jewels, planetary nebulae that mirror each other with an eerie, impossible perfection. Each is the final breath of a sun-like star, a glowing shell of gas blown into space, but these two are not simple spheres. They are shaped with stunning geometric precision, each featuring two long, thin jets of matter shooting in perfectly opposite directions, like the wings of a cosmic butterfly frozen in time. To understand the wonder of this symmetry, we must witness the quiet death of an ordinary star. When a star like ours exhausts its nuclear fuel, its core collapses into a dense, Earth-sized ember called a white dwarf. The outer layers, however, are gently pushed away in a series of pulsating winds, creating a vast, expanding cloud. The ultraviolet radiation from the intensely hot white dwarf then floods this cloud, causing it to fluoresce with brilliant colors. The planetary nebula is born. Most become lovely, chaotic bubbles, but these two in the halo have achieved something far more ordered. Their bipolar jets are flawlessly aligned, shooting out along a single axis for light years into the darkness. This precision is the profound mystery. How does a dying star, in its final chaotic throes, produce such a clean, symmetrical structure? The answer likely lies in what the star left behind. The most compelling theory involves a hidden dance partner. If the dying star was part of a binary system, the gravity of its companion could funnel the ejected gas into two narrow outflows, like placing a thumb over a garden hose. As the star and its partner orbit each other, their combined motion might sculpt the escaping material into those opposing jets. An alternative sculptor is magnetism. The star's own magnetic field, amplified as the core collapses, could act like an invisible cage, channeling the stellar wind out through its poles alone. In both cases, the result is a testament to hidden forces imposing order on chaos. The fact that we see two such nearly identical nebulae in the halo suggests this is not a freak occurrence, but a specific and repeatable phase of stellar death under the right conditions. These twin nebulae are more than just pretty cosmic objects, they are intricate clocks. By measuring the speed of the jets and the expansion of the nebula's shell, astronomers can rewind the explosion, determining exactly when the star died and how quickly it shed its layers. They are fossil records of a star's final moments, revealing the invisible architecture of magnetic fields and gravitational bonds that guided its last breath. In their perfect, mirrored forms, we see not random destruction, but a deeply structured and almost artistic conclusion to a stellar life that lasted billions of years. Three ancient stars in the halo hold a chemical paradox within their light. They possess almost no iron, a hallmark of the universe's first stellar generation, yet they are bizarrely rich in carbon. This specific fingerprint makes them among the most valuable time capsules we have, direct descendants of the very first stars to ever shine. To understand their story, we must journey back to the cosmic dawn. The universe's first stars, often called population 3 stars, were behemoths made of only hydrogen and helium from the Big Bang. They lived fast and died young in colossal supernova, and it was within these first explosions that the universe forged its first heavy elements like carbon, oxygen, and silicon, scattering them into the primordial gas. The next generation of stars, population 2, formed from this newly enriched material. Our trio in Andromeda's halo belongs to this second wave. Their extremely low iron content proves they formed from gas that was seeded by only a handful of those first supernova, before many generations of stellar deaths could build up a diverse mix of elements. But the carbon richness is the real clue. It tells us exactly what kind of first star died to pollute their nursery. Not all early supernovae are created equal. The chemical yield depends massively on the mass of the exploding star. Computer models show that a first-generation star with a very specific mass range, roughly 20 to 140 times the mass of our Sun, would produce an explosion rich in carbon but poor in iron. A star in this range dies in a special kind of supernova where its internal reactions are tuned almost like a factory, churning out carbon in vast quantities before the final collapse. So, the light from each of these three halo stars is a forensic report. It tells us that over 13 billion years ago, A single, specific type of primordial giant died nearby, and its carbon-rich ashes later coalesced into these new suns. They are not just ancient, they are chemical fossils of individual ancestors. Studying them is like finding three distinct pottery shards, each bearing the unique artistic signature of a different, long-lost master craftsman from a forgotten age. They allow us to peer past the homogenized mix of the modern universe and see the raw, uneven output of the first stellar furnaces, one dramatic death at a time. While ancient stars preserve the past, the halo is also receiving deliveries from the future. Two colossal rivers of pure hydrogen gas, each containing the mass of millions of suns, are currently raining down onto Andromeda from the intergalactic void. These are not collections of stars, but vast, diffuse clouds of neutral atomic hydrogen, the raw, uncut fuel of star formation. They were discovered not by optical telescopes, which see only starlight, but by the silent ears of radio astronomy. Hydrogen atoms in space occasionally undergo a subtle quantum flip, emitting a faint but specific radio whisper at a wavelength of 21 centimeters. By tuning giant radio dishes like the Very Large Array to listen for this specific signal across the sky, astronomers can map the location and motion of this invisible gas. The data revealed these two immense structures, each spanning tens of thousands of light years, moving at incredible speeds directly toward Andromeda's halo. They are not orbiting the galaxy, they are in the process of being captured, fresh provisions falling from the cosmic countryside. This capture is a direct glimpse of the cosmic web in action. Our leading model of the universe describes a vast, interconnected filamentary structure of dark matter and gas stretching between galaxies, a cosmic highway system. These two clouds are like dense knots or droplets condensing out of those filaments, finally succumbing to Andromeda's immense gravitational pull after a journey of billions of years. Their significance is twofold. First, they represent the future. Once this cold, neutral gas plunges into the deeper, denser regions of the halo and eventually the galactic disk, it will compress, cool further, and collapse into brilliant new stellar nurseries. This incoming fuel will help spark a future wave of star formation, perhaps hundreds of millions of years from now, ensuring Andromeda's spiral arms continue to shine with young, blue stars long after our own sun has faded. Second, their very existence confirms a critical prediction. Galaxies are not closed systems. They grow not just by eating other galaxies, but by sipping pristine hydrogen from the space between them. This is how they avoid starving and burning through their gas reserves. Finding these clouds in the act of infall is like catching rain in the moment it hits the soil, proving the galaxy is an open system, continuously nourished by the larger cosmos. Yet their journey is perilous. As these clouds fall into the halo, they are entering a hostile environment. They are plowing through a thin, hot plasma that permeates the galactic halo, a gas heated to millions of degrees by supernova shocks and galactic winds. This interaction strips atoms from the cool clouds, creating turbulent wakes and potentially fragmenting them before they reach the star-forming depths. Watching this process unfold in real time, a timescale of millions of years, which is an instant for astronomers, allows scientists to measure the pressure and temperature of the halo's invisible atmosphere. It is a dynamic, violent delivery, a battle between the cold, pristine fuel of creation and the hot, chaotic medium of destruction. These silent, dark rivers falling from nowhere are therefore more than just fuel tanks. They are probes, teaching us about the conditions in the halo and the delicate balance that governs whether a galaxy thrives or slowly fades into a red and dead retirement. The silent hydrogen rivers bring the fuel for future stars, but the halo also holds stars that serve as its most reliable signposts. Among the ancient suns are three distinct types of variable stars, each with its own unique heartbeat, and astronomers use these rhythms to map the vast, dark distances of the halo itself. The first is a Mira variable, a cool, red giant star in its final stages of life. This star doesn't burn steadily. It pulses with a slow, grand rhythm, swelling and shrinking over a period of about 350 days. As it expands, its surface cools and reddens, growing dimmer. As it contracts, it heats up and brightens. This regular, predictable change in brightness is like a cosmic lighthouse flashing on a very long, slow schedule. Because the period of this pulsation is directly linked to the star's true, intrinsic brightness, astronomers can use it as a measuring stick. By observing how faint the star appears from Earth and knowing how bright it truly is, they can calculate its distance with remarkable precision. It's a fundamental ruler for the nearby cosmos. Far more rapid is the pulse of the second star, an Lyrae variable. These are older, smaller stars that have entered a specific phase of helium burning in their cores. They pulsate with a frantic, precise rhythm, brightening and dimming over periods of just hours. Their beat is so reliable and their intrinsic brightness so uniform that they are considered one of the gold standards for distance measurement within our galaxy and its halo. Finding an Lyrae star in the depths of Andromeda's halo is like finding a calibrated beacon in a fog. Its rapid flicker tells astronomers exactly how far away it is, allowing them to pinpoint its location in the three-dimensional volume of that immense sphere. By mapping hundreds of these stars, scientists don't just see a flat picture of the halo. They construct a depth map revealing its true shape, density, and even how it twists and moves through space. The third variable star presents a much more violent kind of change. This is a cataclysmic variable, a binary system locked in a destructive embrace. A white dwarf, the dense corpse of a sun-like star, orbits perilously close to a normal, hydrogen-rich companion star. The white dwarf's immense gravity pulls a stream of gas from its partner, which spirals down onto the dwarf's surface, forming a hot, swirling disk of stolen matter. For a time, this stolen gas simply accumulates, heating up. Then, when the pressure and temperature at the base of this gaseous layer reach a critical point, the accumulated hydrogen ignites in a runaway thermonuclear explosion. The system erupts, increasing in brightness by a factor of 10,000 in less than a day, a brilliant flash in the darkness before slowly fading back to its quiet state over weeks or months. This cycle of theft and detonation can repeat for millennia. While its outbursts are less predictable than the steady pulses of the Mira or Lyrae stars, the peak brightness of these explosions is also a known quantity, another standard candle that can be used to gauge distance. Together, these three variable stars, the slow pulsing giant, the rapid rhythmic beacon, and the explosive thief, form a toolkit. By finding them scattered across the halo, astronomers triangulate the void. They turn a two-dimensional smudge of light into a measured, three-dimensional architecture, proving that this ghostly shell of Andromeda is not a flat screen, but a vast and structured realm we are only beginning to navigate. While variable stars map the halo's vast distances, a far more elusive object haunts its edges, a ghost of pure potential. A massive, distinct cloud of hydrogen gas containing enough raw material to build millions of stars rotates silently in the void. It was discovered by its faint 21-centimeter radio whisper, a signature of cold atomic hydrogen. Yet when every telescope from optical to infrared was aimed at its location, they saw absolutely nothing. No stars, no faint smudges of light, no stellar nurseries, just an immense, dark, spinning mass of pristine fuel. This is a prime candidate for one of cosmology's most speculative and sought-after objects, a dark galaxy. The concept is both simple and revolutionary. A dark galaxy would be a galactic building block composed almost entirely of dark matter and gas, a structure that gathered from the cosmic web but for some critical reason failed to ignite star formation. It would be a fossil from the universe's construction phase, a silent, unfinished blueprint. The rotation of this hydrogen cloud is the key clue. Its motion suggests it is held together by the gravitational grip of something unseen, a halo of dark matter with hundreds of millions of times the mass of our Sun. Without this anchoring mass, a simple cloud of gas would have been ripped apart by tidal forces or dissipated eons ago. The fact that it persists rotating as a coherent entity points to an invisible skeleton. This discovery ignites a fierce debate among astronomers, a classic conflict between two compelling stories. The first story is one of arrested development. This object could be a pristine relic, a dark matter clump that gathered gas from the early universe but never achieved the density or turbulence needed to trigger collapse. Perhaps it was too isolated, never experiencing the gravitational nudges from neighboring protogalaxies that spark compression. Or maybe its gas was kept too warm by the ultraviolet background radiation of the early universe, preventing it from cooling into dense star-forming knots. In this view, the object is a cosmic failure, a would-be galaxy that never lit up, preserved in its infant state for over 10 billion years. The opposing story is less exotic but equally important. Skeptics argue this could simply be a tidal shred, a long ribbon of gas ripped from a visible dwarf galaxy during a past encounter with Andromeda. Such streams are common, but they typically don't exhibit the clean, rotating structure of this object. Could a tidal tail, by some specific geometry, mimic the signature of a coherent, rotating dark galaxy? It is possible, and if true, this object would be a fascinatingly large and intact piece of galactic debris, but not a fundamentally new class of cosmic object. The implications of the first story, however, are profound. If confirmed as a true dark galaxy, it would be a direct validation of a key prediction of the cold dark matter model. That theory suggests large galaxies like Andromeda should be surrounded by thousands of dark matter subhalos. We see only a fraction of that number as visible dwarf galaxies. The missing satellites could be these dark galaxies, clumps that gathered gas but never made stars. Finding one would solve that long-standing puzzle and provide a pristine laboratory to study dark matter's behavior in isolation, free from the complicating effects of stellar winds and supernova. It would be a window into the silent majority of galactic building blocks, the dark foundations upon which the bright universe is built. This ghostly candidate, then, is more than a curiosity. It is a test of our most fundamental ideas about how structure forms in the cosmos, a silent question mark hovering at the edge of perception, waiting to reveal whether it is a forgotten cornerstone or merely a shadow cast by a long-ago collision. A supernova's ghost is racing through the darkness, but its body is missing. This expanding bubble of glowing gas and shock-heated plasma, a supernova remnant, is hurtling through the halo at a staggering speed, leaving its point of origin far behind. The beautiful, lopsided shell tells a story in two parts, a violent death and a long, lonely journey that preceded it. To solve this mystery, astronomers became cosmic detectives, rewinding time with computer simulations. The trail begins with the remnant's shape and motion. It is not a perfect sphere. It is asymmetrical, stretched and compressed, with a brighter, more turbulent leading edge and a longer, streaming tail of cooler debris behind it. This is the classic signature of an object plowing through a medium, like the wake of a speedboat on a lake. By measuring the Doppler shift of the light from different sides of the shell, they could map its three-dimensional velocity. The entire structure, this fossilized explosion, is moving in a specific direction at over 500,000 miles per hour. The next clue was location. This remnant sits in a region of the halo that is sparse and ancient, devoid of the massive, short-lived stars that die as supernova. A star that could produce such an explosion could not have been born here. The only logical conclusion is that the star itself was a runaway. The scenario writes itself. Billions of years ago, in a dense cluster within Andromeda's disk, a massive blue star was gravitationally slingshotted out of its birthplace. This stellar exile, perhaps once part of a tight binary system disrupted by a close encounter, was ejected at high speed, It then spent millions of years on a solitary sprint across the galaxy, traveling hundreds of light years from its home cluster into the desolate halo. All the while, the clock was ticking in its core. Finally, as it sailed through this profound emptiness, its fuel exhausted, it collapsed and exploded in a titanic supernova, far from any familiar constellations, with no stellar siblings to witness its final act. The simulations trace this tragic arc with elegant precision. They take the remnant's current position and velocity and run the cosmic clock backward, subtracting the motion imparted by the galaxy's overall rotation and gravity. The path points like an arrow back to a specific crowded region in the galactic disk, the likely birthplace of the progenitor star. The beautiful, lopsided remnant we see today is therefore a snapshot of two separate events. The inner structure, the complex filaments of oxygen, silicon, and iron, is the frozen geometry of the explosion itself, but the outer shockwave, its distorted bubble, is sculpted by its high-speed journey through the halo's thin gas. It is a tombstone that kept moving, a monument to a life of exile that ended in solitary, spectacular violence. This runaway remnant forces us to reconsider the final moments of such stars. Did the trauma of its ejection alter its internal structure, changing the way it died? And as this glowing shell continues to expand and fade, it will eventually disperse its enriched contents, the carbon for future life, the iron for future planets, not into the busy galactic disk, but into the silent, intergalactic void. Its legacy is a gift of elements cast into the deepest dark, a testament that even the most isolated deaths can seed the cosmos with the ingredients for something new. Its steady pulse is a cosmic heartbeat, but this one beats with a rhythm that defies expectation. Among the halo's stellar metronomes is an ultra-long period Cepheids variable, a star whose brightening and dimming follows a cycle of more than 100 days. This is not a subtle flicker, it is a grand, slow-motion breath of light and heat. That extraordinary period is the key to its identity, for in Cepheid stars, the pace of the pulse is directly tied to its true intrinsic luminosity. A longer period means a vastly brighter star. This particular Cepheid is not just bright, it is a true stellar titan, shining with the light of tens of thousands of suns and containing perhaps 20 times the mass of our own. It is a rare and magnificent beast, and its presence in the desolate galactic halo is a profound puzzle. Cepheids are the mile markers of the cosmos. Their predictable relationship between pulse and power allows astronomers to measure distances across millions of light years. By timing its slow heartbeat and measuring how faint it appears from Earth, we can calculate its distance with remarkable confidence, placing it firmly in the outer halo. But that very location is the mystery. Stars this massive and brilliant are not born in isolation. They form in the dense, gas-rich nurseries of a galaxy's spiral arms, where vast clouds can collapse into such behemoths. They live fast, burning through their nuclear fuel in just a few million years, a cosmic blink of an eye. Finding one so far from any obvious stellar nursery is like finding a newborn elephant alone on a vast, empty plain. It simply shouldn't be there, so how did it arrive? Two compelling stories emerge, each with dramatic implications. The first is a tale of exile. This colossal star may have been born in a bustling cluster within Andromeda's disk, only to be violently ejected by a gravitational encounter with other massive stars or perhaps a black hole. Catapulted out at high speed, it is now spending its brief, brilliant life on a one-way journey into the void, its slow pulse broadcasting its location like a lonely lighthouse in a sea of darkness. The second story is even more radical. Could it have formed in place? This would require a pocket of the halo, an isolated cloud of gas, to have been dense and massive enough to collapse into a single star of such staggering proportions. While almost unthinkably rare, if true, it would force us to expand our understanding of where the universe can forge its most extreme stellar creations. Its future is as dramatic as its present. A star of this mass is destined for a spectacular death. In just a few million years, it will exhaust the hydrogen in its core, begin fusing heavier elements, and ultimately collapse in a supernova explosion so powerful it could outshine its entire host galaxy for weeks. That explosion will seed the surrounding halo with newly forged heavy elements, the iron for future planets, the oxygen for future atmospheres, and likely leave behind a rapidly spinning neutron star or a black hole as its final tombstone. For now, however, it serves a quieter purpose. Its unwavering, slow pulse is a perfect standard candle, helping astronomers calibrate the vast scale of the halo itself. Each measured dimming and brightening is a data point in a three-dimensional map, a fixed point of reference in the shifting dark. This ultra-long period Cephade is therefore both a tool and a riddle, a brilliant anomaly whose very existence challenges our maps of stellar birth and reminds us that even the most established rules of the cosmos have glorious, luminous exceptions. The slow, grand pulse of a Cephade is a steady rhythm, but the halo also holds a star that broadcasts in violent, unpredictable screams. This is an isolated magnetar, a neutron star that elevates magnetic force into the realm of pure cosmic terror. It is a city-sized cinder left over from a supernova, but its true power is not in its density. It is in the magnetic field frozen within it, a field so strong it defies all earthly analogy. To grasp its scale, picture the most powerful magnet you can imagine, perhaps the kind used in medical MRI machines. Now multiply that strength by 10 trillion. That is the magnetic field enveloping this object, a crushing, invisible force that warps the very structure of empty space around it. In such a field, the quantum vacuum itself becomes unstable, boiling with virtual particles that are ripped into reality. If this magnetar were to drift halfway between Earth and the Moon, its magnetic pull would be strong enough to erase the data from every credit card on our planet. It is a level of power that turns physics into a kind of science fiction. This magnetic monster does not rest quietly. Its crust, a lattice of iron nuclei 10 billion times stronger than steel, is under unimaginable stress, perpetually strained by the magnetic field twisting inside it. Occasionally, that crust fractures. These starquakes are events of cosmic magnitude, releasing more energy in a millisecond than our Sun emits in 100,000 years. The quake sends seismic waves rippling across the star's surface, shaking the magnetic field lines anchored there. This violent shaking accelerates particles to near light speed, producing a sudden, blinding flash of gamma rays, the highest energy form of light in the universe. For a fraction of a second, the magnetar outshines every other source of gamma rays in the entire Andromeda galaxy, a scream of pure energy echoing across 100,000 light-years of darkness before fading back into silence. Its presence in the desolate halo is the central mystery. Magnetars are thought to be born from the most massive, rapidly spinning stellar cores. They are the product of a specific, violent kind of supernova where conditions align to amplify the dying star's magnetic field to these insane levels. Such extreme stars are born in the dense, bustling stellar nurseries of the galactic disk, not in the quiet outskirts. So how did this one end up in profound isolation? The answer is written in its speed. Measurements show it is moving fast, a celestial bullet fired from the galactic core or a dense cluster. The supernova that created it was almost certainly asymmetrical, giving the newborn neutron star a tremendous kick. This kick was its exile, propelling it clear of its birthplace and its own supernova remnant, sending it on a solitary voyage into the halo's emptiness. For hundreds of thousands of years, it has traveled through this void, its unimaginable magnetic field its only companion, occasionally cracking under its own internal strain to send a pulse of radiation through the cosmos that reminds any potential observers of the terrifying forces that lurk unseen in the dark. That magnetar's violent energy is a product of the galactic core, but the halo also cradles a sleeping giant of creation. Drifting in the profound cold is a colossal, dark nebula, a giant molecular cloud containing the mass of 10 million suns. This is not a wisp of atomic hydrogen, but a deep, dense reservoir where hydrogen has paired up into molecules, the coldest and most stable form of raw star-forming fuel. It is a cosmic iceberg adrift in a warm sea, a nursery that has yet to birth a single star. Its existence so far from the galactic disk is a profound stillness, a pause in the universal cycle of life and death. Molecular clouds like this are the cradles of solar systems, but they require specific, sheltered conditions to form. Atomic hydrogen must cool and find a dust grain to cling to, allowing two atoms to meet and bond into a molecule. This delicate process is easily destroyed by energetic ultraviolet radiation from hot, young stars, which can rip the molecules apart. So how does this immense cloud survive, exposed in the halo's emptiness? It has built its own fortress. The cloud is not just gas, it is laced with a fine, dark dust of carbon and silicate, grains no larger than particles of smoke. This dust acts as a phenomenal shield. It absorbs the destructive ultraviolet photons that permeate intergalactic space, allowing the deep interior of the cloud to remain in a state of profound cold, only a few degrees above absolute zero. Within that shielded heart, the gas grows denser and more complex. Molecules like carbon monoxide form, and gravity begins its slow, patient work. But here in the halo, that work is stalled. Star formation requires not just cold, dense gas, but also a trigger, a shock wave from a nearby supernova, the gravitational nudge of a passing galaxy, or the turbulent collision of two cloud fragments. In the serene isolation of the halo, such triggers are vanishingly rare. The cloud simply floats, a frozen potential, its immense mass held in a state of suspended animation. This presents a cosmic question about its future, a fork in the road written by gravity. One path leads toward rejuvenation. The cloud is not in a stable orbit. It is slowly, inexorably responding to Andromeda's gravitational pull. Over the next few 100 million years, it may spiral inward, eventually plunging into the bustling galactic disk. There, it would encounter the very pressures and shocks it has avoided for eons. Compressed by galactic tides and rammed by other gas clouds, its dormant cores would suddenly collapse, igniting a spectacular firestorm of star formation, a delayed, brilliant bloom of light from fuel gathered in the deepest dark. The other path is one of eternal quiet. Perhaps its trajectory will keep it in the halo's outskirts forever, or maybe the thin, hot plasma that permeates the galactic halo will slowly erode it, stripping away its outer layers molecule by molecule over billions of years until it dissipates into a faint, warm mist. This giant, dark cloud is therefore a story waiting for an ending. It is a reminder that the universe is filled not just with what is, but with what could be. It holds within its dark heart the possible futures of countless solar systems, the potential for planets, oceans, and life, all contingent on the gentle, patient, and utterly indifferent forces of gravity and time. Will it remain a silent monument to unspent potential, or will it one day become the brilliant, chaotic engine of a new stellar generation? Its fate is a secret it keeps, hidden behind its veil of cosmic dust. Two dead suns are locked in a final, silent embrace, a binary dance that can only end in cosmic fire or unimaginable density. This pair of white dwarfs, each the Earth-sized core of a long-dead star, orbit each other not in the bustling disk but in the halo's quiet expanse. Their waltz is not eternal. With every rotation, they lose a minuscule amount of energy, radiating it away as ripples in space-time called gravitational waves. This loss is causing their orbit to shrink, an imperceptible tightening that will, over millions of years, draw them into a catastrophic merger. We can calculate this fate with remarkable precision. By measuring their orbital period and estimating their masses from their subtle gravitational tug on each other, astronomers can apply the equations of general relativity. The math reveals a clock ticking down in the dark, predicting a collision on a cosmic timescale perhaps in another 100 million years. This slow-motion countdown presents two radically different destinies, and the total mass of the pair decides which path they take. If their combined mass stays below a critical threshold, about 1.4 times the mass of our Sun, their merger will be violent but not apocalyptic. The lighter, larger white dwarf will be torn apart by the gravity of its denser companion, its material forming a swirling disk that rains down onto the survivor. This influx of fresh fuel, primarily carbon and oxygen, could ignite a final, furious burst of nuclear fusion on the surface of the remaining white dwarf, creating a brilliant but temporary nova outburst. The system might survive, now as a single, more massive white dwarf, shrouded in the glowing remains of its consumed partner. The second fate is one of total, universe-shaping destruction. If the combined mass of the two white dwarfs exceeds that critical limit, their merger triggers something far more profound. As they spiral together and finally collide, the sudden, immense compression and influx of material raises the core temperature to billions of degrees almost instantly. This triggers runaway carbon fusion not on the surface but throughout the entire merged object. In a heartbeat, there is no force in the universe that can counteract the outpouring of energy. The entire binary system is completely obliterated in a thermonuclear detonation of staggering scale, a Type Ia supernova. This standardized explosion is so bright it can outshine an entire galaxy, and its consistent peak brightness makes it a vital milepost for measuring cosmic distances. Every atom of iron in your blood, every speck of calcium in your bones, was forged in such an explosion long ago and scattered across the cosmos. There is, however, a speculative third possibility, a fate even more extreme than total annihilation. What if the combined mass is so extraordinarily high, perhaps approaching twice the mass of our Sun? In that scenario, the merged object might be so heavy and hot that even a supernova cannot blow it apart. Instead, the immense gravity could overcome the last possible force of resistance, crushing the entire mass not into a white dwarf, but into something even denser, a neutron star. This would be a star dying twice, its corpse collapsing into a new, more exotic form of corpse. The formation of a neutron star from white dwarf mergers is a theoretical frontier, a possibility that challenges our understanding of stellar endpoints. This binary pair drifting in the halo is therefore a frozen moment before a cosmic decision. It is a system poised between becoming a brilliant beacon for measuring the universe or transforming into one of its densest possible objects. Their quiet, decaying orbit is a prelude to an event that will, in a distant future, either seed the halo with new elements or leave behind a silent, ultra-dense sentinel as its only monument. These three ancient suns are solitary storytellers, each a hermit drifting in the halo's expanse with a unique chemical tale etched into its light. They belong to the population 2 generation, the second wave of stars born after the universe's first giants died, but they are not part of any cluster or stream. Their isolation makes them pure samples, uncontaminated by later mergers, and by reading their elemental signatures, astronomers can reconstruct the specific supernova that seeded their birth clouds billions of years ago. The first star is a study in surprising balance. Its spectrum reveals it is extremely poor in iron, as expected for such an ancient object, but it shows a remarkable, even enrichment of lighter elements like carbon, oxygen, and magnesium. This pattern is the chemical fingerprint of a specific kind of death. It points to a first-generation progenitor star that was massive, perhaps 20 to 30 times the mass of our Sun, but not so massive that it collapsed directly into a black hole. This star lived its brief life and then died in a relatively well-mixed supernova, one that thoroughly churned and expelled its newly forged elements in a roughly even ratio. The cloud that later collapsed to form this halo star was painted with a broad brush of many elements at once, a balanced foundation for the cosmos. The second star tells a story of violent specialization. Its light shows an extreme overabundance of elements like strontium and barium, which are created not in the initial supernova blast, but in the intense neutron-rich environment that occurs in the seconds before the explosion or in the merging of neutron stars. This star's chemistry suggests its birth cloud was polluted by the debris of a rare kind of supernova, one where the progenitor star's core was rapidly spinning or where the explosion itself was highly asymmetric, producing a flood of free neutrons that slammed into lighter nuclei to build these heavier elements. It is the signature of a dramatic, messy death that selectively enriched the cosmos with specific, exotic atoms. The third star presents the cleanest signal of all. It is almost purely carbon-enhanced. Its iron content is vanishingly low, but carbon is thousands of times more abundant relative to iron than in our own sun. This is the clearest clue of all. It points to a first-generation star of a very specific mass range that ended its life not with a traditional supernova, but with a pulsational pair instability event. In this scenario, the star becomes so hot in its core that matter and antimatter particle pairs are spontaneously created, robbing the core of pressure. This causes the star to undergo violent, repeated pulses, each one ejecting a shell of material rich in helium-burning products like carbon before the core finally collapses. This star, then, formed from the carbon-rich ashes of one of these pulsating giants. Together, these three solitary stars are like 3 pages ripped from different chapters of the same ancient history book. One records a balanced foundational explosion, another captures a rare neutron-rich event, the third is a pure product of a pulsating, unstable demise. By comparing them, astronomers do not see a smooth, uniform early universe. Instead, they see a patchwork quilt of chemical enrichment, where the fate of a single, massive star could dictate the entire elemental makeup of the next generation of suns in its neighborhood. These stellar fossils prove the first steps toward building a complex cosmos were taken not with uniformity, but with spectacular, individual variety. A silent collision has recently reshaped a distant frontier of the halo. In one of its outermost regions, astronomers have mapped a vast, turbulent scar, the aftermath of a high-velocity cloud slamming into the galaxy's sparse gaseous atmosphere at over 600,000 miles per hour. This was not a gentle merger but a cosmic car crash, an event of raw, elemental force that left a clear fingerprint in the radio and X-ray sky. The evidence is a telltale shock front, a sharp boundary where the thin, hot plasma of the halo has been violently compressed and heated to millions of degrees by the incoming bullet of cold, dense gas. On one side of this invisible line, the gas is quiet and diffuse. On the other, it is a churning maelstrom of energy, its atoms excited and ionized by the sudden, immense pressure of the impact. Computer simulations bring this ancient event to life, tracing the physics of the collision frame by frame. They show the massive intergalactic cloud, perhaps a fragment of the cosmic web itself, on a trajectory that has crossed the void for billions of years. As it finally enters the halo's influence, it meets resistance, the galaxy's own tenuous atmosphere. The leading edge of the cloud crumples like a piece of paper hitting a wall, sending powerful shockwaves rippling both forward into the cloud and backward into the halo. These shockwaves are the architects of change, compressing gas to densities it hasn't known since the galaxy's formation. In their wake, something remarkable may be stirring. Dense, cold knots begin to condense out of the turbulent chaos, cores of hydrogen and helium growing heavy enough for their own gravity to take over. This is the spark of triggered star formation, a wave of new suns being ignited not by the quiet collapse of an isolated cloud, but by the violent, propagating pressure of a colossal impact. It is star birth by cosmic concussion. These events are vital deliveries for the galactic ecosystem. The incoming cloud is a shipment of pristine hydrogen, untainted by the heavy elements forged in previous stellar generations. This fresh gas dilutes the enriched mix of the existing halo, providing the raw, unprocessed fuel needed to forge a new population of stars with a unique chemical signature. But the impact does more than just deliver fuel, it stirs the pot. The immense energy of the collision sends ripples through the halo's material, mixing gases of different temperatures and densities, potentially disrupting the orbits of ancient star clusters and even disturbing the dark matter distribution on a local scale. It is a dynamic reminder that the halo is not a static museum, but a living, breathing part of the galaxy, subject to occasional violent weather from the intergalactic medium. This impact site, then, is a snapshot of galactic growth in action. It shows us that galaxies are not islands, but open systems, continually accreting fresh material from the vast cosmic ocean around them. Each such collision is a chapter in the story of a galaxy's ongoing construction, a burst of chaos that can seed the darkness with new light. Light from a cosmic cataclysm is still arriving long after its source has gone dark. A brilliant flare from a quasar, the active, superheated heart of a galaxy billions of light years behind Andromeda, erupted in the distant past. That single flash of light has been traveling through the universe for eons, but its journey was not a straight line. As it approached the Andromeda-halo, it passed through the warped space surrounding a massive, invisible object. The gravity of this foreground mass acted as a natural telescope, bending the light and creating not one, but several distinct images of that same quasar flare, each arriving at Earth at a slightly different time. This is a light echo, a ghostly replay of a single event made possible by one of the universe's most elegant phenomena, strong gravitational lensing. Think of it like a sound echo in a canyon. You shout once, but the sound waves bounce off different rock faces, reaching your ears as multiple delayed repetitions. Here, space-time itself is the canyon wall. The immense mass of the lensing object curves the fabric of the universe, creating separate paths for the light to travel. One image might take a relatively direct route, while another is bent on a longer, scenic detour around the gravitational well. The time delay between the arrival of these images can be days, weeks, or even years, giving astronomers a slow-motion replay of the quasar's outburst from different angles. The identity of the lens itself is the central puzzle. What in the halo has enough concentrated mass to warp light so dramatically? The prime suspect is an incredibly dense, ancient globular cluster, one so packed with stars that its combined gravity creates a significant dent in space-time. Alternatively, and more mysteriously, the lens could be a nearly pure knot of dark matter, a concentration of the invisible stuff with very few stars to give it away. By meticulously measuring the separation and brightness of the multiple quasar images, and by timing the delays between them, scientists can literally weigh the lensing object. They can map its mass distribution with precision, determining whether it is compact like a star cluster or more diffuse like a dark matter subhalo. This single, delayed flash of ancient light is therefore a triple tool. It reveals the violent history of a quasar far in the background. It probes the distribution of mass, visible or not, in Andromeda's halo. And it demonstrates with beautiful clarity that gravity is not just a force that pulls on planets. It is a sculptor of reality, bending the very paths that light must follow, turning the cosmos into a hall of mirrors where the past continually echoes into the present. A single, brilliant point of warmth glows in the cold infrared sky, yet it reveals nothing to our other eyes. This unidentified infrared source in the halo shines with the heat of a hidden furnace, but when telescopes search for it in visible light or the high-energy glare of X-rays, they find only an empty silence. It is an object defined by what it hides, a beacon that only broadcasts in the language of heat. To decode its secret, we must consider what can produce such intense infrared radiation while remaining otherwise invisible. The first possibility is a dying star wearing a thick final shroud. Imagine an aging giant in its last stages, perhaps a Mira variable or a red supergiant that has begun to expel its outer layers in a slow, dusty wind. This ejected material, rich in carbon and silicate grains, forms a vast, opaque cocoon around the star. The star's visible light is completely absorbed by this cosmic soot, but the dust grains themselves heat up, re-radiating that absorbed energy as a strong, warm glow in the infrared. We would see a warm point, but the star at its heart remains completely veiled, its final acts playing out behind a curtain of its own making. A second, more violent story is that of a failed supernova. This theory suggests the object could be the remnant of a massive star that collapsed directly into a black hole without the brilliant, element-forging explosion we expect. In this scenario, the star's outer layers might fall back onto the newborn black hole, forming a swirling, incredibly hot accretion disk of gas and dust just outside the event horizon. This disk would be shrouded in debris, glowing fiercely in infrared from friction and compression, but emitting little visible light and only specific, hard-to-detect X-rays. It would be a cosmic burial, a star vanishing into darkness with only a warm afterglow to mark its passing. A third, and perhaps most intriguing, possibility involves not a death but a birth. The source could be a massive, dense circumstellar disk orbiting a hidden, newborn object, a protostar or even a young brown dwarf, a failed star too small to ignite sustained fusion. In the halo's isolation, a pocket of gas might have quietly collapsed. The resulting object would be cool and faint, but the disk of material still falling onto it would be heated by the violence of accretion, producing a strong infrared signature. The central object itself might be too dim and cool for our optical telescopes, while the dusty disk blocks any direct view, leaving only the telltale warmth of its construction site. This single point of infrared light, therefore, is a lesson in the limits of a single perspective. It screams its presence in one wavelength and is a ghost in all others. Its mystery can only be unraveled by the combined power of multi-wavelength astronomy, where radio telescopes might map its cold outer structure, infrared observatories measure its heat, and future, more sensitive X-ray instruments listen for the faintest whisper of high-energy processes. It is a stark reminder that the universe is a multi-sensory experience, and to view it through only one window is to miss most of the story. This unseen furnace challenges our categories, asking whether it is a funeral pyre, a silent collapse, or a hidden nursery, all while offering no easy answer except the persistent, warm glow of its secrecy. Within a river of stolen stars, a new island is being born. This dense, brilliant knot of young blue stars and glowing gas, embedded within one of the halo's vast tidal streams, is not a remnant of destruction but a potential site of creation. It is a tidal dwarf galaxy in the act of formation, a cosmic phoenix rising from the ashes of a galactic collision. To understand this reversal of fortune, we must revisit the violent process that made its home. When Andromeda tore apart a smaller dwarf galaxy billions of years ago, it didn't just stretch the victim's stars into a long stream. It also wrenched out immense amounts of cold, dense hydrogen gas. Within that ejected ribbon of gas, gravity found pockets of instability. As the stream settled into its orbit, regions of higher density began to pull in more material from their surroundings. Gas compressed, cooled, and finally reached the critical threshold for collapse. In this one particular knot, the conditions were just right, and the first brilliant, massive stars ignited. Their fierce, ultraviolet radiation now ionizes the surrounding gas, making the entire region glow like a neon sign in the cosmic dark, while their stellar winds and eventual supernova will further sculpt and enrich this newborn stellar nursery. This presents a profound shift in our narrative. galactic mergers are typically stories of consumption and death, where the larger galaxy devours the smaller. But here, within the debris of that very act, we see the potential for new, independent life. The collision provided not just the raw materials, but also the trigger, the shock waves and compression necessary to jumpstart star formation in an otherwise quiescent cloud. It is a demonstration of the universe's complex cycle, where destruction and creation are two sides of the same coin. The future of this glowing knot, however, hangs in a delicate balance. Will it become a true bound dwarf galaxy, or will it simply be a temporary spark in the stream? The answer depends on a cosmic tug of war. On one side is its own self-gravity, the mutual attraction of all the gas and stars within the knot, trying to pull it together into a stable, enduring island. On the other side are the disruptive tidal forces of Andromeda itself, the same gravity that created the stream, which now constantly pulls and shears at the object, trying to tear it apart and re-assimilate it. The outcome hinges on mass and distance. If the knot has managed to gather enough material, perhaps hundreds of millions of solar masses, its own gravity may be strong enough to withstand the tidal stretching. Over time, as more gas cools and forms stars, and as the stellar population ages and mixes, it could coalesce into a stable, rotating system with its own distinct identity, a true dwarf galaxy orbiting within the halo, born from the wreckage of its predecessor. But if it is too lightweight, or if it orbits too close to Andromeda's core where tidal forces are strongest, its fate is dispersion. The young stars will slowly drift apart, their shared motion insufficient to bind them forever. They will simply blend back into the broader stellar stream, their brilliant blue light fading as they age, leaving behind only a temporary flare of youth in the archaeological record. Astronomers watch this object with particular fascination because it is a real-time test of galaxy formation theory. By measuring its total mass, its star formation rate, and the motions of its stars relative to the stream, they can run the calculations forward, predicting its fate. Is this how some of the smaller galaxies we see today originally formed, not from primordial gas in the early universe, but from the recycled debris of later giant collisions? This glowing knot challenges the simple story of galactic evolution, suggesting that even in the aftermath of a cosmic cataclysm, the universe retains a stubborn impulse to build, to gather chaos into new, temporary orders, and to write new beginnings in the light of young stars at the very edge of an ancient giant's domain. Its gravitational heartbeat is a violent, rhythmic scream of X-rays, a binary system locked in a feeding frenzy on the edge of the halo. This is an X-ray binary, a pair where a dense stellar corpse, either a neutron star or a black hole, orbits a normal hydrogen-rich star. The corpse's immense gravity is a relentless thief pulling a stream of gas from its living companion. This stolen material doesn't fall quietly. As it spirals down at nearly the speed of light, it forms a swirling, superheated disk around the invisible predator, a maelstrom of plasma heated to millions of degrees. It is from this tiny, furious disk that the system screams its presence, blazing with high-energy X-rays that cut through the halo's darkness. The rhythm of these X-ray pulses reveals the system's orbital period, the time it takes for the two objects to complete one full dance around each other. But the true mystery isn't the scream itself, it's the shape of the dance. This binary does not trace a neat, circular path. Its orbit is wildly elliptical, a stretched oval that brings the two stars breathtakingly close before flinging them far apart. At its closest approach, or periastron, the stellar corpse dives deep into the outer atmosphere of its companion, violently stripping gas and triggering an intense flare of X-rays. Then, as it swings out to the orbit's distant apex, the feeding slows to a trickle, and the X-ray signal nearly vanishes, only to build again as the inevitable, deadly embrace approaches once more. This bizarre, lopsided orbit is a profound puzzle. In a typical X-ray binary, the two stars are thought to settle into a nearly circular orbit over time. their movement smoothed by tidal forces and the transfer of mass between them. A highly elliptical orbit like this is a sign of a traumatic past, a gravitational scar that has not yet healed. Astronomers have two leading theories for how such a wound was inflicted, each a story of cosmic violence. The first story involves a disruptive guest. This binary may have originally been a peaceful, circular pair until a third object, another star, or even a black hole passed too close in the dense stellar environment of its birthplace. This gravitational interloper would have given the system a powerful kick, perturbing its stable orbit into an elongated, eccentric ellipse before being flung away into the darkness. The binary, forever changed, was then itself ejected from the crowded galactic disk, carrying its new, lopsided dance into the halo's isolation. The second story is one of a violent birth. It focuses on the moment the stellar corpse itself was created, when a massive star dies in a supernova to form a neutron star or black hole. The explosion is almost never perfectly symmetrical. If more material is ejected in one direction than another, the conservation of momentum acts like a rocket engine, giving the newborn compact object a tremendous natal kick. This kick can be so powerful it disrupts the orbit of any surviving companion star, instantly transforming a circular path into a highly elliptical one. In this scenario, the binary system we see today is the direct result of that ancient explosion's asymmetry, a permanent record of the supernova's directional fury. The orbit's extreme shape also dictates the system's long-term fate. That intense, periodic close pass does more than just trigger X-ray flares. Each close encounter creates powerful tidal forces that subtly drain energy from the orbit, very slowly circularizing it over hundreds of millions of years. Furthermore, the act of stealing mass itself transfers angular momentum, another force that works to calm the orbit's wild swings. This system, then, is caught in a slow act of gravitational relaxation. We are witnessing it not in its serene, circular old age, nor in the immediate chaos of its birth or disruption, but in a dramatic, middle-aged phase where its traumatic history is still written clearly in its path through space. By precisely timing the X-ray pulses and modeling the orbit's subtle decay, astronomers can effectively rewind the cosmic clock. They can estimate the strength of the natal kick or the mass of the intruding star that caused this chaos, and they can predict how many more violent close passes remain before the dance settles into a quieter, more predictable rhythm. This screaming binary is therefore more than a source of high-energy radiation. It is a forensic laboratory. Its strange orbit is a piece of evidence, allowing us to reconstruct a cataclysm that occurred millions of years ago, a silent event that left behind only this lopsided waltz and a regular, hungry scream as its enduring testimony. Two stars are in the process of leaving the universe we know. These extreme velocity outliers are not merely escaping Andromeda's gravity. They are moving with such immense speed that they will break free from the gravitational pull of our entire local group of galaxies, a cluster that includes Andromeda, the Milky Way, and about 50 other smaller galaxies. Their trajectories are not orbits, they are exit vectors pointing directly out into the boundless intergalactic void. To understand the force required for such a feat, picture our galactic neighborhood as a deep, wide valley. Most stars are like rolling hills within that valley, bound by its slopes. These two outliers are like stones launched with such force from the valley's deepest point that they arc over the highest ridge and never fall back, destined to sail over an endless plain. Tracing their paths backward through space is an exercise in cosmic forensics, and all evidence points to a single, terrifying origin: the chaotic, supermassive black hole at the very heart of the Andromeda galaxy. This monster, containing the mass of over 100 million suns, is the only engine in the local group powerful enough to act as a gravitational slingshot of this magnitude. The most likely scenario involves a doomed dance. Each of these stars was once part of a tight binary system that wandered too close to the black hole's event horizon. In a violent gravitational maneuver, the black hole captured one star into a tight, doomed orbit, while flinging its companion away at a significant fraction of light speed, a process theorists call the Hill's mechanism. The ejected star receives a kick so profound it overcomes the gravitational bonds of its entire galactic family. Their fate is one of profound and permanent solitude. Once they cross the boundary of the local group, perhaps in another 100 million years, they will enter a realm of staggering emptiness. The space between galaxy clusters is so vast that, from the perspective of one of these stars, the universe would transform. The familiar, cloudy band of the Milky Way would shrink to a faint smudge. Andromeda would become a distant, fading spiral. All the galaxies of the local group would coalesce into a single, receding patch of light in an otherwise black sky. A sky where the next island of stars might be tens of millions of light years away. They will become true intergalactic wanderers, sailing on courses that may never again bring them close to another star or planet. This raises a hauntingly beautiful question about resilience. Could these stars have carried their planets with them? If their planetary systems survived the violent ejection, those worlds would now experience a reality beyond our comprehension. Their sun would be a fixed, unwavering point in an ever-darkening sky, a private star for a world traveling between galaxies. For any hypothetical life on such a world, the concept of a galactic night sky would slowly vanish, replaced by an eternal, starless dark punctuated only by the faint, fading glow of abandoned island universes. These two runaway stars are more than just fast-moving points of light. They are emissaries. They carry with them the chemical signature of Andromeda's core, a fingerprint of elements forged in that dense, ancient environment. As they travel into the void, they broadcast that signature into the cosmic wilderness, a silent message in a bottle cast into the darkest ocean imaginable, on a journey that will last longer than the future existence of the very galaxy that expelled them. Planetary systems were not born in the modern, metal-rich universe alone. Three ancient suns drifting in the halo with their extremely low metal content have been found to harbor worlds of their own. These are not gas giants like Jupiter, but smaller, denser planets, likely rocky or icy bodies that formed from the universe's most basic ingredients. Their existence forces a complete rewrite of planetary formation theory. For decades, the prevailing wisdom was clear: you need dust. Planets form from the swirling disks of gas and dust that surround newborn stars, and that dust is made of heavy elements: silicon, carbon, iron, magnesium, the very things astronomers call metals. Without a sufficient amount of this dusty grit, the microscopic particles cannot stick together, cannot build pebbles, then rocks, then planetesimals, and finally planets. It was thought a certain metallicity threshold was an absolute requirement. These three halo stars, with their pristine, metal-poor composition, should have been barren. Yet the subtle wobble in their light, the telltale dip in their brightness, confirms they are not alone. They carried the seeds of planets within them from the dawn of time. So how did they do it? The answer may lie in a colder, slower, and more patient process. In a disk with very little dust, the traditional model of sticky collisions might indeed fail. But there is another powerful force at work: gravity. In the frigid outer regions of such a primordial protoplanetary disk, ices of water, methane, and ammonia could have frozen solid. These ice grains, while still scarce, might have been more sticky than their dusty cousins. More importantly, in the absence of much solid material, the disk itself could have developed gravitational instabilities. Vast swaths of gas swirling around the infant star could have directly collapsed under their own weight, rapidly forming giant planetary cores in a single dramatic step. This process bypasses the need for slow dust accumulation, forging worlds directly from the gas and ices available. The planets around these ancient stars, therefore, are likely a different breed from our own. They might be predominantly icy worlds, vast frozen spheres with rocky cores, similar to the enlarged versions of Jupiter's moons Ganymede or Callisto. Or, if the gravitational instability was efficient, they could be rocky planets born from the scant dust that did exist, but built on a foundation of primordial hydrogen and helium worlds with thick, ancient atmospheres we can scarcely imagine. Their discovery stretches the timeline for potential life in the cosmos back by billions of years. If rocky worlds could form around some of the very first stars, then the chemical building blocks for life, carbon, oxygen, nitrogen, were also present, forged in that first generation of stellar explosions. The universe may have become habitable not in its middle age, but in its raw, violent youth. These three silent solar systems, each a fossilized snapshot of the universe's first experiments in planet building, now drift in the halo. They are proof that the impulse to create worlds is a fundamental part of cosmic evolution, a process that began with the barest of materials in the deepest dark, long before our own sun was even a glimmer in the galactic disk. A vast, invisible sphere of pure energy hangs in the galactic dark. This is the gamma-ray bubble, a faint but immense structure in the halo detected not by optical telescopes, but by instruments that see the universe's most violent light. Gamma rays are the product of the most extreme processes in nature, particles accelerated to nearly the speed of light, slamming into gas or each other. Finding such a high-energy bubble in the halo, a region we think of as quiet and ancient, is like discovering a roaring, invisible fire in the middle of a frozen, silent plain. It has no obvious central engine, no brilliant quasar or exploding star at its heart. Its glow is diffuse, uniform, and utterly mysterious, forcing astronomers to consider three radically different stories for its creation. The first story looks to the galaxy's violent past. At the center of Andromeda sits a supermassive black hole, currently quiet and dormant. But what if millions of years ago it woke up? A period of intense feeding, as vast clouds of gas fell into the abyss, could have triggered a cataclysmic outburst. Jets of relativistic particles moving at nearly light speed would have shot out from the black hole's poles, punching through the galaxy's disk and inflating two colossal bubbles into the halo above and below the galactic plane. These bubbles, filled with fast-moving particles, would slowly expand and fade. Over eons, the visible shockwaves and hot gas would dissipate, but the high-energy particles trapped within might still be there, spiraling in magnetic fields and colliding to produce the faint, lingering gamma-ray glow we see today. This would make it a fossil of Andromeda's last great eruption, a ghost of central engine activity from an era long before human history. The second story draws a direct parallel to our own home. Our Milky Way has its own giant gamma-ray structures called the Fermi bubbles, extending from its core. They are thought to be the result of either a past black hole outburst or a period of intense star formation in the galactic center that created a powerful wind of energetic particles. The bubble in Andromeda's halo could be a perfect analog, a twin structure that tells us such energetic feedback is a common, perhaps universal, phase in a large galaxy's life. It would mean that the quiet, stately spirals we see today are all recovering from energetic outbursts in their recent cosmic past, their halos still ringing with the faint, high-energy echo of those events. The third story is one of collective power from countless tiny engines. The bubble might not be a single structure at all, but the combined glow of thousands of millisecond pulsars, neutron stars spinning hundreds of times per second. These cosmic flywheels are incredibly efficient particle accelerators. Their rapid rotation and immense magnetic fields generate powerful winds of electrons and positrons that flood into the surrounding space, colliding with starlight and the cosmic microwave background to produce gamma rays. If the halo is seeded with a vast, unseen population of these ancient, spinning cinders, their individual faint emissions could blend together into the uniform glow of the bubble. This explanation would reveal the halo not as a graveyard, but as a hidden hive of incredibly dense, energetic activity, a realm dominated by the quiet, persistent spin of dead stars. Each origin story paints a different picture of the halo's true nature. Is it a museum for past cataclysms, a standard feature of galactic weather, or a hidden metropolis of spinning stellar corpses? The answer lies in the bubble's detailed shape and spectrum. A fossil jet bubble might be slightly elongated or show signs of a preferred axis. A wind-blown bubble might be more symmetrical and correlate with other signs of past star formation. A pulsar-made bubble would have a very specific energy signature in its gamma-ray light. Untangling this signal from the background noise of the cosmos is a monumental task requiring years of painstaking observation. This silent, invisible sphere of high-energy light is therefore a question written across 100,000 light-years. It asks us to reconsider what quiet really means in the life of a galaxy, reminding us that the frontier is not always still sometimes. Its deepest silence is the hum of a forgotten engine, or the chorus of a billion spinning dead stars, still broadcasting their power in a language only the most patient instruments can hear. Its orbit is a cosmic contradiction. While the vast majority of objects in Andromeda's halo swing around the galactic center in one consistent direction, following the grand rotation of the galaxy itself, this one globular cluster moves defiantly against the flow. It is a counter-rotating star cluster, a dense ball of ancient suns that travels a backward path, and its rebellion is a clue written in motion. This isn't a random act of celestial defiance, it is the preserved momentum of a long-dead galaxy. When two galaxies merge, they don't just mix their stars like paints. They bring with them the specific direction and speed of their original orbits. If a smaller galaxy approaches Andromeda from a particular angle, perhaps nearly head-on or from a steeply inclined path, its entire entourage of star clusters will inherit that unique motion. As the dwarf galaxy is shredded by tidal forces, its clusters are set adrift, but they retain that original directional signature like a fossilized compass needle. This backward-moving cluster is one such fossil. It was not born in Andromeda's halo, it was stolen. By measuring its precise velocity and trajectory, astronomers can rewind the cosmic clock. They trace its path backward not to a point within Andromeda, but to a region of empty space where a small galaxy once traveled on a doomed retrograde orbit. This allows them to reconstruct the merger event itself, the approximate size of the victim galaxy, the angle of its approach, and even a rough estimate of when the catastrophic encounter occurred, perhaps 2 or 3 billion years ago. The cluster's survival is equally telling. A globular cluster is a gravitationally tight family, a city of stars so densely packed that it can withstand the tidal forces that tore its parent galaxy apart. As the dwarf galaxy was stretched into streams, this cluster remained intact, a solitary piece of architectural salvage from a demolished cosmic building. Its very presence, orbiting stubbornly backward, is a living record of that demolition. It tells us that Andromeda's growth has not been a neat, orderly process of gathering material from one direction. It has been a messy, chaotic history of collisions from all angles, a galactic pinball game where incoming victims can arrive from any trajectory, leaving behind captured objects that remember their original heading. This single cluster, therefore, is more than a celestial oddity. It is a dynamic archive. By studying its chemical makeup, scientists can compare it to other clusters in the halo. Does it have a unique elemental signature different from Andromeda's native clusters? If so, that confirms its extragalactic origin and even hints at the specific chemical history of its lost parent galaxy. Its backward orbit is a permanent label, a tag that reads foreign, ensuring it will never fully blend into the halo's population. It is a captured ambassador from a galaxy that no longer exists, forever circling its captor while holding onto the last memory of its true home. A silent hole in the cosmic scaffold has been found. In a specific region of Andromeda's vast halo, the gravitational-lensing signal simply vanishes. The background galaxies beyond it are not stretched and warped as they should be. Their light passes through this zone relatively undisturbed. This is a dark matter dropout, a place where the invisible mass that should dominate the halo appears to be missing, a ghost that has left the room. The discovery flips our expectations entirely. We have spent our journey finding places where dark matter clumps or concentrates, but this is a place where it has seemingly been cleared away. The lensing map, which usually shows hills and valleys of mass, shows a flat plain, a gravitational pothole in the fabric of the halo. Three compelling theories attempt to explain this absence, and each challenges a different piece of our cosmic understanding. The first story is one of cosmic billiards. Could a massive collision have scattered the dark matter here? Imagine another galaxy, or a giant subhalo of dark matter itself, plowing through this region in the distant past. Just as the gravitational slingshot can fling stars out of the galaxy, it could also impart enough energy to the dark matter particles in this zone to kick them out, effectively blowing a hole in the dark matter distribution. The collision would have been a silent, invisible event, but its aftermath would be this cleared-out region, a temporary cavity in the dark matter sea that might take billions of years to refill. The second story is far more radical, questioning the nature of dark matter itself. Our standard model assumes dark matter is cold and collisionless, meaning its particles interact with each other and with normal matter only through gravity, not through any other force. This allows it to form smooth, extensive halos, but what if dark matter has a hidden complexity? What if its particles can interact with each other through some unknown force, a kind of dark electromagnetism? In that case, dark matter could have a fluid-like behavior. Perhaps in this region, such interactions cause the dark matter to dissipate energy, allowing it to collapse into an even denser, more compact knot that our current lensing surveys cannot resolve. The dropout wouldn't be an absence, but hiding a pooling of dark matter so tight it looks like a void at our current resolution. The third story brings the problem back to the world of visible matter. Gravitational lensing measures total mass, both dark and normal. Could our assumption about the normal matter here be wrong? We see very few stars in this region, so we assume there is very little normal or baryonic matter. But what if it holds a significant amount of extremely hot, diffuse gas or a population of rogue planets and brown dwarfs too faint to detect? This unseen baryonic component would contribute to the gravity, meaning we would need less dark matter to explain the total. The dropout might not be a lack of dark matter, but an overestimation of how much should be there because we missed a portion of the ordinary stuff. This quiet region of missing gravity is therefore a critical stress test. It pits our models of galactic dynamics, particle physics, and baryonic astronomy against each other. Is it a scar from a forgotten impact, a hint of dark matter's secret social life, or a lesson in our own observational blindness? The answer will not come from staring into the emptiness, but from building ever more sensitive maps of the halo's invisible terrain, searching for the subtle contours that will tell us what truly lies within and what has truly gone. A faint primordial glow stains the darkness of the halo, a cloud of hydrogen so immense it could swallow galaxies whole. This is a Lyman alpha blob, a structure typically found in the farthest, earliest reaches of the cosmos, and its presence here in our own galactic backyard is a profound anomaly. It does not shine with the light of stars. Instead, its hydrogen atoms are being constantly bathed in intense ultraviolet radiation, causing their electrons to jump to a higher energy state and then fall back, emitting a very specific crimson wavelength of light known as Lyman alpha. The entire cloud fluoresces like a cosmic neon sign, a soft, monochromatic beacon in the void. The central mystery is not the glow itself, but the hidden ultraviolet lamp that powers it. Astronomers face three competing possibilities, each pointing to a different, unseen engine in the darkness. The first theory is one of hidden, furious birth. Perhaps within the heart of this diffuse cloud, a colossal burst of star formation is taking place, completely shrouded by dust. Thousands of the hottest, most massive stars could be burning there, their fierce ultraviolet light absorbed by the surrounding gas and re-radiated as the Lyman alpha glow we see. This would make the blob a hidden stellar factory of unimaginable scale, a secret nursery veiled behind its own brilliant fluorescence. The second theory looks to a more central, violent power. Could the ultraviolet flood be coming from a quasar, the active supermassive black hole at Andromeda's core? While the core is currently quiet, a past outburst could have sent a flash of UV light racing through the halo. That light, traveling for millions of years, might only now be illuminating this distant primordial cloud, causing it to glow like a ghostly echo of the galaxy's ancient fury. We would be seeing a delayed reaction, a cloud lighting up in response to a scream from the center that fell silent eons ago. The third and most serene explanation removes Andromeda from the equation entirely. This blob may simply be a cold, pristine cloud of hydrogen left over from the galaxy's formation, and it is being illuminated by the ambient ultraviolet glow that fills the entire universe, the combined light of every quasar and galaxy since the dawn of time. This cosmic background radiation is faint, but for a cloud of sufficient size and density, it could be enough to trigger a detectable Lyman alpha glow. In this story, the blob is a passive screen reflecting the universal light of all creation. Finding such a structure in Andromeda's halo is a direct challenge. Lyman alpha blobs are cornerstones of our models of the early universe, where giant clouds of gas were common and easily lit up by the first brilliant galaxies and quasars. But in the modern, evolved universe, such vast, pristine clouds should have long since collapsed into stars or been heated and dispersed. This object is a relic that has somehow persisted for over 10 billion years, a floating fragment of the cosmic dawn that never received the memo that the party was over. It is a living fossil, and by studying what illuminates it, we are not just solving a local puzzle. We are testing the conditions of the entire cosmos, measuring the strength of the universal UV background, and probing the violent history of our nearest galactic neighbor, all through the soft, crimson light of a hydrogen atom's quiet whisper. A pair of dead stars are spinning down a countdown to collision. This binary neutron star system is a cosmic clockwork of unimaginable density, where two city-sized spheres, each heavier than our sun, whirl around each other every few hours. One of them is a millisecond pulsar, spinning over 500 times every second, its lighthouse beam of radio waves sweeping past us with metronomic precision. This incredible speed is not its birthright, it is a stolen inheritance. This pulsar was born from a supernova, likely spinning a few dozen times per second fast, but not extraordinary. Its transformation came from a long, destructive relationship. In its youth, it orbited a normal, bloated companion star. As that star evolved, it expanded, and its outer layers spilled over onto the neutron star. This incoming stream of matter did not fall quietly. It carried with it a tremendous amount of angular momentum, the spin of the donor star's rotation. As this material spiraled onto the neutron star's surface, it transferred that spin, acting like a cosmic whip, accelerating the pulsar to its dizzying millisecond rhythm. Astronomers call this process recycling. A dead star is revived, spun up by consuming its partner. The donor star, stripped of its outer layers, eventually collapsed in its own supernova, leaving behind the second neutron star we see today. The result is this pristine, ultra-clean laboratory. Two ultra-dense orbs, one spinning furiously, the other likely slower and more magnetic, dancing in a vacuum nearly free of contaminating gas. Their dance is not eternal. With every orbit, they lose a tiny, precise amount of energy, radiating it away as gravitational waves ripples in the fabric of space-time itself. Einstein's theory of general relativity predicts this energy loss with exquisite detail, and by timing the pulses from the recycled pulsar, astronomers can measure the orbital decay. The two stars are spiraling inward by about a millimeter per orbit, an imperceptible drift that will, over tens of millions of years, bring them into a final, catastrophic merger. This makes the system a future gravitational wave source, a prelude to an event that will shake the universe. But for now, it serves as one of the most precise testing grounds for gravity ever discovered. The pulsar's clock-like pulses allow scientists to track every nuance of the orbit. They can measure the subtle precession of the orbit, how space-time is dragged around by the spinning masses, and even test whether the gravitational constant has remained unchanged over cosmic time. Any deviation from the predictions of general relativity would appear as a tiny hiccup in the pulsar's timing, a clue to new physics hiding in the extreme gravity of a neutron star's embrace. This silent, spinning pair is therefore both a monument to stellar cannibalism and an instrument of profound discovery. Its rapid ticks counting down not just to a distant collision, but toward ever deeper truths about the fundamental forces that weave our cosmos together. A galaxy can be immense yet almost invisible. Orbiting Andromeda is a satellite so large it rivals our own Milky Way in sheer physical size, spanning tens of thousands of light years. Yet it contains so few stars that its total light output is less than 1% of our galaxies. This is an ultra-diffuse galaxy, a ghost of a structure so transparent you could look right through it to see the universe beyond. If you were standing on a planet within it, your night sky would be a hauntingly empty expanse, dotted with only a handful of faint, ancient suns separated by gulfs of darkness so vast the concept of a Milky Way would be unimaginable. The profound mystery is not its faintness but its very existence. How does something so fragile, so spread out, hold itself together against the relentless tidal forces of its giant neighbor, Andromeda? According to the laws of gravity and motion, a structure this sparse should have been torn apart and dissolved into the halo eons ago. The only force powerful enough to act as a cosmic glue is an immense invisible anchor. This galaxy must be absolutely dominated by dark matter. Its few visible stars are merely accidental ornaments on a colossal, unseen sphere of mass, a deep gravitational well so vast it keeps the entire delicate tapestry from unraveling. These objects have earned nicknames like ghost galaxies or see-through galaxies, and they are more than just curiosities. They are extreme laboratories that test the limits of our understanding. Their discovery forces a critical question. If dark matter is so abundant here, forming a halo massive enough to protect billions of stars worth of space, why did so few actual stars form? It presents a story of arrested development, a galactic blueprint where the dark matter scaffold was built, but the star-forming gas never properly condensed or was stripped away early on by ultraviolet radiation or galactic tides. This leaves behind a cosmic paradox, a galaxy-sized footprint with only a village's worth of light. Finding such a ghost orbiting Andromeda changes our senses of the cosmos. It suggests that what we see when we look at the night sky, the brilliant spirals and ellipticals, might be only the brightest successes. For every grand galaxy like the Milky Way, there could be dozens of these silent, dark matter-dominated phantoms, the true but invisible majority of galactic structures, drifting through the cosmic dark as permanent monuments to the universe's unseen foundations. Its violet glow is the last meal of a forgotten star, a lone stellar mass black hole containing perhaps 10 times the mass of our Sun drifts silently through the halo. It is invisible, but it is not alone. Around it swirls a faint, hot disk of superheated gas and dust, the final, fading remains of a star that ventured too close years or even centuries ago. This is the aftermath of a tidal disruption event, one of the most violent acts a black hole can perform. The story begins with an ordinary star, perhaps similar to our own, on a long, looping orbit that fatefully brought it within the black hole's Roche limit. This is the point where the black hole's tidal gravity pulling on the near side of the star becomes stronger than the star's own gravity holding itself together. The star did not fall in whole. It was stretched, a process called spaghettification, into a long, thin strand of stellar material. Part of this stream was flung away into the darkness, while the rest wrapped around the black hole, forming a swirling, chaotic accretion disk. In that disk, temperatures soared to millions of degrees, causing it to blaze with X-rays and ultraviolet light as the stellar debris spiraled toward the event horizon. What we see now is the quieting of that storm. The brilliant flash of the initial disruption has long since faded, traveling across space for perhaps 100 years before reaching our telescopes. The disk is now a dimmer, steadier glow, still hot from friction and compression, but running out of fuel. It is a dying campfire built from the ashes of a sun. This fading light is our only window onto the black hole itself, allowing us to estimate its mass and spin from the behavior of the gas in its final death throes. The profound question this object raises is about the victim. Where did that star come from? It was likely a native of the halo itself, one of the ancient metal-poor stars that have orbited there for billions of years. Its entire life, from its birth in an early cosmic cloud to its long, quiet journey through the dark, ended in a single, cataclysmic moment of gravitational violence. It was a star that survived the chaotic construction of the galaxy, only to meet its end in the dark, silent grasp of a wanderer. This black hole, with its faint, hot disk, is therefore a monument to a very specific kind of encounter. It tells us that even in the sparse halo, where distances between objects are immense, orbits can still intertwine over cosmic timescales, leading to sudden and total destruction. It is a reminder that the darkness is not empty, but threaded with invisible wells of gravity, each capable of ending a stellar life with a silent, final pull, leaving behind only a faint, warm glow as its only epitaph. Its pulse is a familiar rhythm in an unexpected place, but the message it sends is garbled. This Cepheid variable star does not reside in the open field of the halo or the bustling disk. It is embedded directly within one of the long, graceful rivers of stars that are the shredded remains of a devoured galaxy. On its own, that is not unusual. Streams can carry all types of stars. The profound mystery lies in its light. Cepheids are the universe's most reliable mile markers. They possess a strict mathematical relationship between their pulse and their power. The longer the period of their brightening and dimming, the greater their true, intrinsic luminosity. By timing the pulse, astronomers know exactly how bright the star should be. By measuring how faint it appears from Earth, they can calculate its distance with remarkable confidence. For this star, the math produces a contradiction. Its period suggests it should be a brilliant beacon, but its observed brightness is far too dim for its location in the stream. According to the standard ruler, it is either much farther away than every other star in that stellar river, or it is fundamentally less luminous than its pulse declares it should be. This anomaly strikes at the heart of cosmic cartography. If our most trusted distance measuring tool is giving a faulty reading here, what does that mean for our maps of the entire universe, which are built upon the light of Cepheids in faraway galaxies? Astronomers are investigating this celestial paradox like detectives at a crime scene with three primary suspects. The first possibility is a case of mistaken identity. Perhaps this is not a classic Cepheid at all, but a different type of pulsating star that mimics the rhythm. Certain classes of variables, like anomalous Cepheids or even some types of eclipsing binary stars, can have similar periods but vastly different intrinsic brightnesses. If it belongs to one of these other families, then the period-luminosity relationship does not apply and the mystery dissolves. the star would simply be a quieter singer using the same tempo as a much louder one. The second suspect is cosmic blending. Could the light we measure be contaminated? Imagine this Cepheid is in a tight binary system with a much fainter, cooler star, or perhaps it lies directly along our line of sight to a distant background galaxy. The light from the two sources blends into a single point in our telescopes. We are timing the Cepheid's pulse correctly, but the extra, steady light from its companion makes the combined object appear brighter than the Cepheid alone. When we plug that total brightness into our equations, the distance calculation becomes skewed, placing it incorrectly. Untangling this requires ultra-sharp observations, looking for subtle spectral signatures of a second star or using techniques to resolve the light into its components. The third and most far-reaching possibility is that our fundamental ruler needs recalibration. Could the environment of the stellar stream itself be altering the star's behavior? This Cepheid was born in a different galaxy, one with a unique chemical composition. Its pulse depends on the intricate physics of its interior, which is influenced by the exact mix of elements in its core. If its home galaxy had an unusual chemical history, perhaps it was very rich in helium or very poor in metals like iron, that could subtly change the internal mechanics of its pulsation, tweaking the period-luminosity relationship just enough to throw off our measurements. This would mean our universal ruler is not perfectly uniform. It might have slight regional variations based on a star's ancestral home. Solving this puzzle is more than academic. It forces us to check our work on the largest scales. If this one anomalous Cepheid points to a hidden flaw in our methods, it could have a ripple effect, subtly shifting the measured distances to other galaxies, and by extension, our calculation of the expansion rate of the universe itself. This quiet, misfit star in a river of ghosts is therefore a single discordant note that asks us to listen more carefully to the cosmic symphony, to ensure the rhythms we trust are truly as universal as we believe. A final whisper from the cosmic dawn has been caught in the halo's darkness. This is not a star, a planet, or any solid object. It is a cloud, a vast and tenuous reservoir of gas detected only because it floats directly between us and the brilliant beacon of a distant quasar. As the quasar's light journeys for billions of years to reach our telescopes, it passes through this cloud. Atoms within the cloud absorb very specific wavelengths of that light, leaving dark, narrow lines in the quasar's spectrum like a chemical barcode. For nearly every cloud we've ever found, that barcode is rich and complex. It shows the fingerprints of dozens of elements: carbon, oxygen, silicon, iron, all the products of stellar furnaces. But for this one cloud in Andromeda's halo, the barcode is almost blank. The spectrum shows the strong, clear lines of hydrogen and helium, the two primordial elements forged in the Big Bang itself. And then nothing. Where there should be a forest of dark lines marking heavier elements, there is only empty space. This cloud appears to contain no detectable metals whatsoever. It is a pocket of the universe that has never been touched by a star's death. Finding such a relic is a triumph of patience and precision. Astronomers must first identify a brilliantly bright, distant quasar that happens to lie directly behind the Andromeda-halo from our perspective. They then collect its light with the world's most powerful telescopes for hours, sometimes nights, to gather enough photons for a superbly detailed spectrum. They analyze that spectrum line by line, comparing it to laboratory measurements of every known element, searching for the telltale dips in light that indicate absorption. In this case, the absence of those dips is the stunning result. The purity it suggests is staggering. To have absolutely no contamination from supernova means this cloud has existed in profound isolation for over 13 billion years. It must have formed in a quiet backwater of the early universe, a region where no massive stars were born to die and pollute it. It then had to avoid being swept into any galaxy during the chaotic period of structure formation. and it had to survive for eons in the halo without mixing with even the trace amounts of enriched gas that permeate intergalactic space. It is a cosmic bubble, a perfect vacuum-sealed sample of the raw material from which everything we see, every star, every planet, every one of us was ultimately made. This object stands as the ultimate control sample for the universe. Every other thing we study, from the oldest stars to the newest planets, is a product of chemical evolution. They are mixtures, alloys of the primordial stuff with the ashes of dead stars. This cloud is the pure ingredient before the mixing began. Studying its temperature, density, and internal motions tells us about the conditions of the neutral gas from which the first structures condensed. It lets us test our models of the universe's infancy with a physical benchmark, but its existence also poses a beautiful and humbling question. If such pristine material can still be found, floating like a ghost in our neighbor's halo, what does that say about the completeness of the cosmic cycle of life and death? We think of galaxies as great engines of recycling, churning through gas, forging elements, and scattering them back out. This cloud is a reminder that the process is not total. Some fragments of the beginning have slipped through, unchanged and unsullied, carrying the signature of a time before time had any history at all. It is a silent, gaseous monument to the universe's first moment, a breath of the original cosmos held in suspension, waiting in the dark for us to finally read its simple, elemental story. The ultimate mystery is a star that hides its light but radiates a secret warmth. Our final object is a star in the halo whose behavior defies easy classification, presenting a signature so strange it has sparked the most profound question we can ask. Are we looking at nature's most elaborate construction or something else entirely? In visible light, this star is remarkably dim, as if shrouded, but in the infrared, it blazes with an intense, unexpected heat. This combination, a deficit of visible starlight and a massive surplus of infrared radiation, is the exact pattern theorists predicted decades ago for an object of unimaginable scale and ambition, a Dyson Sphere. The concept proposed by physicist Freeman Dyson is not a solid shell, but likely a vast swarm of orbiting energy collectors, a megastructure built by a civilization to capture nearly all the output of its home star. The star's light would be absorbed by the collectors and converted into usable energy, with the waste heat from their operations radiating away as the infrared glow we detect. It is the hypothetical endpoint of technological growth, a civilization's entire star enclosed by a tapestry of its own making. The sheer scale is humbling. To build such a thing requires harnessing the resources of entire planets, mastering engineering across astronomical distances, and thinking on timescales that dwarf human history. Finding even a candidate is a moment that echoes across centuries of wonder. Yet, before we let our imagination soar, we must first be ruthless cosmic detectives. The universe is a master of mimicry, and nature provides several powerful, if less thrilling, explanations. The leading natural candidate is a colossal, thick ring of dust and debris. Picture a star surrounded by a cloud of shattered planets and asteroids from a cataclysmic collision in its distant past. A cloud so dense and close in that it blocks the star's visible face but is warmed by its hidden light, re-radiating that energy as infrared. Alternatively, the star could be in a rare and brief transitional phase, like a late-stage red giant that has puffed off an immense, opaque shroud of gas and dust, hiding its core while the surrounding material heats up. There are also exotic stellar remnants, like a white dwarf accreting material from a dusty disk, that could produce a similar signature. Astronomers are now engaged in a careful process of elimination, using every tool at their disposal. They search for specific chemical signatures in the star's faint visible light that might indicate a natural dusty environment. They look for subtle variability in its output, which a rigid megastructure might not exhibit but a chaotic debris cloud would. They map its surroundings for any traces of ejected material or companion stars that could explain the phenomenon. This investigation is a perfect portrait of the scientific method at the frontier, hope balanced with skepticism, wonder tempered by evidence. So, is it a Dyson Sphere? The honest answer is that it is overwhelmingly more likely to be a rare natural object than an alien megastructure. But that sliver of possibility, that remote chance, is why we look. This candidate, whether it is ultimately a dust-cloaked star or something beyond our current understanding, represents the culmination of our journey through the halo. It embodies the very reason we explore these strange and silent frontiers. We are not just cataloging curiosities, we are searching for context, for meaning, and for answers to the oldest questions. Are we a cosmic accident or part of a broader pattern? Is the universe, for all its violent beauty, ultimately a lonely place? The halo, with its rogue planets, dark matter ghosts, and ancient stellar fossils, has shown us that the cosmos is far stranger and more wonderful than we dreamed. And if, against all odds, one of those 50 strange objects ever whispers a signal not of physics, but of purpose, it would change everything. The search itself, the act of looking into the dark and wondering what else might be looking back, is what makes us human. Our journey ends here at the edge of the known, peering into the infrared glow of a mystery, reminded that the greatest discovery still waiting in the halo's vast and silent dark may not be an object at all, but a new understanding of our place within it all. These 50 objects are a testament to the universe's boundless creativity. From the solitary rogue planet sailing through eternal night to the silent, spinning dance of binary neutron stars, each one tells a different chapter in the epic story of Andromeda. This is not an empty frontier. The halo is a galactic archaeological site, a layered record of cosmic history written in starlight, dark matter, and the faint echoes of ancient violence. Every faint smudge, every silent gravitational tug is a clue. It holds the pristine fuel of the Big Bang in untouched clouds, the scattered bones of devoured galaxies in stellar streams, and the furious, dying breaths of stars that exploded in profound isolation. We have wandered through a gallery of cosmic extremes, where the laws of physics are stretched to their limits, and the line between natural wonder and something more becomes beautifully blurred. The next time you look up at that faint, fuzzy patch in the constellation Andromeda, know that you are not just seeing a distant spiral. You are looking at a giant surrounded by ghosts, each one a mystery waiting to be solved. Which of these 50 strange wanderers captured your imagination the most? Was it the dark galaxy candidate, a structure that might be made of almost nothing we can see? Or the hypervelocity star, a sun on a one-way journey out of the galaxy forever? Let us know in the comments below. If you want to keep exploring the deepest mysteries of the cosmos, be sure to subscribe. Our journey through the strange and silent places of the universe has only